From the start of genus Homo's 2 million-year history, humans have participated in armed conflict. Humans are not special in this regard either. In Conrad Lorenz's On Aggression in 1963, he writes that violence within a species was not only common, but necessary for access to a limited amount of resources and females. So in that vein, herbivores fight just like lions and humans. For 99.5% of this 2 million-year history, until the rise of states, humans have lived in small hunter-gatherer societies which have participated in a continuous cycle of raiding and being raided. Although no written artifacts are found from this time period, ancient societies often found warfare as a way to demonstrate strength and power, relying on rituals, myths, and religious beliefs to justify their actions and predictions. Although warfare prediction methods have come a long way since our divination beginnings as hunter-gatherers, the derivative purpose of warfare predictions have remained constant throughout history, to calculate the likelihood of victory. As new weapons and scientific progress emerged, the landscape of warfare drastically evolved with it, forcing military thinkers to update their prediction models while simultaneously looking for historical trends and rules of thumb. Most of these predictions were often based on intuition and past experience, and the advent of applied mathematics and statistics in the field of warfare is still a relatively recent invention. In looking at the evolution of warfare predictions, I would like to first take a look at the oldest recorded military treatise that we still have, Sun Tzu's Art of War, written during the Warring States period of ancient Chinese history. It contains observations and insights into crucial factors that shape the direction of warfare and is still taught in modern military academies today. It shows how similar the fundamental predictive model of warfare is across generations, and also provides a glimpse into the underlying uncertainties that still plague commanders in modern-day conflicts. In Chapter 1, titled Initial Calculations, Sun Tzu lays out 5 factors that govern warfare: Tao, heaven, earth, commander, and method. The latter 4 are interpreted to have similar definitions to seasons, or the environment, terrain, leadership, and management. Tao has many different interpretations in Chinese philosophy, but is mostly translated as the way, which refers to the larger flow of nature that all humans are a part of. Could this not be a variable representing unaccounted uncertainties? Sun Tzu expands this model in the following chapters, including factors of information intelligence, knowing your enemy, knowing yourself, the relative size of armies, and strategies employed. Although these are all crucial factors that still dictate the outcome of modern warfare, Sun Tzu's Art of War does not allow us to quantify any of the above variables, and therefore we are left to rely on intuition and experience rather than empirical data or analysis. The expansion of warfare prediction utilizing empirical methods came in Europe during the 18th and 19th centuries. Advancement in mathematics and statistics during this time allowed military strategists to begin using empirical data and analysis to predict the outcomes of conflicts and prepare accordingly. Examples of this can be seen in Lazare Carnot and Sebastian Vauban's advances in the bastion fort construction, where geometric calculations were made to prevent dead zone angles where enemies could hide from gunfire atop the fort. At the same time, the uncertainty of warfare and the multitude of variables that contributed to an outcome were further articulated as a significant force in conflicts. Karl von Clausewitz, a Prussian general and military theorist, asserted that war is not just a mechanical process, but a complex and dynamic social phenomenon that is shaped by a range of factors, including politics, culture, and psychology. He argued that war is inherently unpredictable and that no amount of planning or preparation could eliminate this uncertainty. Clausewitz also asserts an additional type of uncertainty, which he coins the fog of war. This refers to the confusion, uncertainty, and chaos that often characterizes the battlefield, making it difficult for commanders to make accurate assessments and decisions. Clausewitz argued that the ability to navigate this fog of war is a key factor in determining success or failure on the battlefield. Therefore, in rudimentary terms, Clausewitz has answered a lot of the parameters involving a general warfare prediction model. Our models on war will never be fully accurate, like Newton's theory of gravity, due to the unquantifiable nature of human uncertainty that determines the outcome of war. Sun Tzu's inclusion of information as a crucial factor in conflict also highlights another form of uncertainty. The complete logistics of enemy and battle spaces are never truly known, and therefore arises another prediction error within the larger equation of war outcomes. During World War I, the widespread use of mathematical and statistical methods helped eliminate certain aspects of uncertainty while also evolving the battle space to include new variables. Statistical analysis examining the distribution of artillery shells fired and adjusting for factors such as wind speed and distance allowed models to estimate the location of enemy artillery positions and help guide counter-battery fire. The development of aircraft during World War I also led to the need for new mathematical models to analyze the trajectories of aircraft in flight. Frederick William Lanchester first proposed the Lanchester-type equation in his book Aerial Warfare, which was published during World War I in 1916. In his book, Lanchester used the equations to model the behavior of military forces in aerial combat and demonstrated that the outcome of a battle was not simply a function of the number of aircraft on each side, but depended on other factors such as the skill of the pilots and the quality of their equipment. Since then, Lanchester-type equations have been applied to a wide range of military scenarios, from ground warfare to naval warfare, and have become a valuable tool for military planners and analysts. These innovations continued into World War II, where mathematical and statistical models tried to solve for human and intelligence uncertainties, most notably seen with the development of the Enigma machine by the German military. The Enigma machine was used to encrypt and decrypt military communications, making it difficult for Allied forces to decipher enemy messages. The Allies developed a number of mathematical models to try to crack the Enigma code, including the use of statistical analysis to identify common patterns in intercepted messages. In addition to cryptography, other forms of mathematical modeling were also used to reduce warfare uncertainty by employing statistical analysis, such as looking at patterns in U-boat attacks on Allied ship convoys in order to predict better the location and timing of future attacks. Not only were calculations of intelligence uncertainty getting more accurate, methods of intelligence gathering also became more accurate. The development of radar technology allowed military planners to detect incoming aircraft and ships from larger distances than before, while aerial reconnaissance provided detailed information on enemy troop movements and military installations. One of the biggest breakthroughs in warfare prediction during World War II is the novel additions of game theory, specifically in the context of strategic bombing. The concept of game theory was developed by mathematician John von Neumann and economist Oscar Morgenstern in their 1944 book, Theory of Games and Economic Behavior, which analyzed mathematical models of decision-making in situations where two or more parties have conflicting interests. This concept was applied to the development of the bombing game by the Rand Corporation, where the game was a simulation model that allowed military planners to analyze the effectiveness of different bombing strategies against specific enemy targets and find the optimal way to allocate resources to bombing missions, taking into account factors such as the cost of aircraft and munitions, the expected damage to enemy targets, and the risk of losing aircraft to enemy fire. Although human uncertainty is not reduced in this model, expectations of human uncertainty could be constructed to better aid commanders' decision-making. Since World War II, the development of computer technology has led to significant advances in the use of simulations for military predictions. Computer-based simulation models allow military planners to simulate and analyze a wide range of military scenarios, taking into account factors such as troop movements, supply lines, and the terrain of the battlefield. Today, simulation modeling is a key component of modern military decision-making, and these models incorporate advanced mathematical and statistical analysis, as well as other forms of modeling and simulation techniques to provide military planners with a comprehensive understanding of the likely outcomes of different military actions. One such advancement is the use of machine learning called classification trees. This approach involves creating a decision tree that identifies key factors that contribute to the outcome of a battle, using a set of training data which includes information on the terrain, weather, troop strength, and other factors that might affect the outcome. Once the decision tree has been constructed, it can be used to predict the outcome of future battles based on the same set of factors. For example, if military planners have information on the terrain, weather, and troop strength for an upcoming battle, they can use the decision tree to predict the likely outcome of that battle. This allows military planners to make more informed decisions based on data-driven analysis rather than relying on intuition or guesswork. However, there are still limitations on our current models of military prediction. One of the main challenges is that it can be difficult to accurately predict the outcome of battles based on a limited set of factors. Factors that are very difficult to quantify and predict, such as the morale of troops or quality of leadership, still play a big role in determining the outcome. The accuracy of the model is also heavily biased by the training set data, and if military tactics or technology have evolved since then, the model may not accurately predict the outcome of current battles. So that begs the question, how accurate are our current warfare model predictions? It turns out, in some areas, we have come a long way and completely eliminated uncertainty, while in others, there are still heavy biases in our predictions. On February 24th, 2022, Vladimir Putin ordered a full-scale invasion into Ukraine. As the Washington Post writes, math was not in the Ukraine's favor. Russia had more troops, more tanks, more artillery, more fighter jets and guided missiles, and had demonstrated in previous conflicts its willingness to pummel its weaker adversaries into submission, with no regard for the loss of civilian lives. Kyiv might not fall as quickly as the Russians expected, the Americans concluded, but it would fall. Saturday, May 6, 2023 marks the 437th day of the ongoing Russia-Ukraine conflict. Rapid evolutions in the Russia-Ukraine war redefined how the war was being fought, and as a result, significant new factors contributed to the model of war outcomes. This is what some people now call the new generation of conflict prediction, algorithmic warfare. Using a digital model of the battlefield, commanders can penetrate the notorious fog of war. Applying artificial intelligence to analyze sensor data, NATO advisors outside of Ukraine can quickly answer essential questions of combat which were once uncertain to a commander. Where are the Allied forces? Where are the enemy? Which weapons will be most effective against enemy positions? They can predict and deliver precise enemy location information to Ukrainian commanders in the field. And after an action, they can assess whether their intelligence was accurate and update the system. As we can see, warfare prediction models have come a long way since humans first tried to grasp the art of war 2 million years ago. Although much of our advances concerns eliminating archaic uncertainties from our predictions, both primary sources of uncertainty, human and intelligence gathering, will never be fully eliminated. Furthermore, aside from the question of accuracy, there's also a larger question of implementation that should be addressed. According to the Washington Post, the American government started noticing signs of an impending military attack on Ukraine starting in October 2021 and promptly notified President Zelensky and other allied nations. But as Zelensky defends, you can say a million times, listen, there may be an invasion. Okay, there may be an invasion. Will you give us planes? Will you give us air defenses? Well, you're not a member of NATO. Oh, okay, then what are we talking about? Even with such an accurate prediction looming over Ukraine, the true date of Russia's invasion was still a large uncertainty that could not be minimized. Advances in combat prediction will never be able to fully account for the human agents that decide specifics in warfare, which begs the question of how predictions should be interpreted and implemented in this field. President Zelensky argues that if he revealed the specific information from President Biden to the public months before the war, fear and chaos regarding the future of Ukraine would have plunged the economy and exchange rate, unintuitively decreasing their chance at victory. Zelensky recalled, if we had communicated that, then I would have been losing $7 billion a month since last October, and at the moment when the Russians did attack, they would have taken us in 3 days. As warfare is an evolving human process, predictions on warfare have to constantly evolve as well, and predictions in the future in this area must always be mindful of its bias and the contingency of its prediction on certain assumptions. As many former generals have alluded to in their writings, war might be seen more as an art than a science.